Thank you, Kevin. And the thing they noticed about the photoelectric effect was that a higher intensity of light didn't make you more likely to dislodge an electron. It was the frequency of the light that would dislodge electrons. That is, if light had a high enough frequency, it would dislodge electrons. If the light didn't have a high enough frequency, it wouldn't dislodge the electrons. Whereas you would think that, just the higher the intensity of the light, the more electrons you dislodge, but it didn't work that way. All that mattered was the frequency of the light, having it be blue light rather than red light, or have it be X-rays rather than ultraviolet. And so Albert Einstein came along, just one second, and made these postulations. He said that light consists of little particles, little packets of energy called photons. These photons have no mass, but they do have energy. And the energy of a photon is equal to Planck's constant. This man named Max Planck, who had done work with black body radiators, which essentially Albert Einstein used his work to make his conclusions, multiplied by the frequency of the light. And when I use light, now I'm kind of thinking in terms of just the electromagnetic wave. It doesn't have to be visible light. It can be infrared, ultraviolet, X-ray, whatever. And so we tend to write it like this: E equals HF. That's the energy of a photon, or Planck's constant. And you will find Planck's constant on that little half sheet in the packet we got. Planck's constant is 6.6. I'm going to use 6.63 times 10 to the negative 34 joule seconds. Or you can also convert it to electron volts, 4.15 times 10 to the negative 15 electron volts seconds. You people who've had AP chemistry, have you seen this equation before? Yeah. Okay, and do they call it HF or do they call it something else? Yeah, that's the way I learned it, was H nu. I prefer H nu, but our textbook uses HF, so I'm going to use F for frequency, even though I like nu. Hey, what's nu? Well, now here's what Einstein says happens with the photoelectric effect. Now we don't have to think in terms of waves. We can think in terms of little photons. And the photon hits the metal surface and is completely annihilated, and all of that energy of the photon is given over to the electron that's, what do you call, released from the metal, that's dislodged from the metal. Part of the energy of the photon is spent in dislodging it. That's called the work function of the metal. And any energy of the photon left over is given to that electron as kinetic energy. So let me show you the photoelectric effect equation. Which, do I have, here, let me look at my little sheet. Yeah, I do have it there. Number 4. Photoelectric effect. The energy of the photon, some of it is spent in the work function, that is, the energy required to dislodge the electron, and then the rest of it is given over into kinetic energy of the electron. And they say maximum kinetic energy because, maybe not all of it is given to kinetic energy, maybe it's given in some other thing. But that's the maximum kinetic energy of any dislodged electron. it's kind of like if you wanted to go to a club and you're gonna buy a bunch of alcohol in this club, and that alcohol costs money. I don't know if did you stop it just then?
No.
Okay, good. You know, you're gonna go to a club and you're gonna want to buy lots of alcohol and spend a lot of money, but it costs money to get into the club. So once you spend your money to get into the club, whatever money you have left over, you can spend on alcohol. Then you can, you know, spend hundreds or maybe even thousands of dollars, and you had a really good time. Okay. So let's go ahead and answer some of these questions. Number one, the definition of the photoelectric effect. Hit a metal surface with high enough energy light, and the metal emits what?
Electrons.
Yeah, electrons. And you know what these electrons are called? They get a special name, these electrons that come off. They're called photoelectrons. So write that in the next open space. They're called photoelectrons because they got ejected by light. Number two, in 1905, Albert Einstein explained the photoelectric effect. He said that light of frequency F can be regarded as a collection of discrete packets of energy called what? Photons. Yeah, they're called photons. Yeah, just call them photons. Yeah, you're thinking of energy levels, I think, of electrons. But, and those electrons, when they fall to a lower energy level, that's the swan size. Okay, each having energy E equals HF, where H is Planck's constant, and that's given. Look at number three. When a photon hits the metal surface and dislodges an electron, the photon is what?
Annihilated.
Yes, destroyed. Or if you know how to spell annihilated, it's annihilated. And all of its energy is used to eject the electron. Any energy left over provides the electron, the ejected electron, with kinetic energy, just like this formula says. So now, believe it or not, you guys are ready to do example number one. The minimum work required to eject an electron from a particular metal is 4.73 electron volts. Find the minimum frequency of light needed to eject the electrons from this metal. Well, before I go any further, if you want to get the energy of a photon, and I tell you I want the energy in electron volts, which version of Planck's constant do you suppose you're going to use? The one with joules or the one with electron volts? Yeah, please do example number one now.